Hey guys, today we're going to introduce the idea of work and power. So, work is, by definition, the product of the displacement and the force component parallel to the direction of travel. So, that's a lot of words that are super sciencey sounding. So, essentially, what it means is we are multiplying the force parallel to the direction of travel times the displacement or distance the object travels. So this equation right here, we have work, W, equals force parallel. So these are two little parallel signs, just kind of like that's perpendicular. That means parallel. So work equals force parallel to the distance traveled. So technically we are taking the force that we are applying, and as long as it is parallel to the motion, we are multiplying it by the distance that the object travels. In metric units, work is measured in Newton meters, which means newtons times meter, and a special name is given to this unit, the name joule. So just like energies that we learned about, this unit is the same. So work and energy are both measured in joules. Since our equation is very specific and it's force parallel to the direction times the distance, that means that force can be exerted on an object and yet no work is done at all. And there are two examples of this. The first example, if the object does not move. So we can apply a force all day, but if the object does not travel any distance, then the work is negligible. We can ignore it. The second example is if our force is perpendicular to the distance traveled. So an example like this would be if you are walking down the street holding an ice cream cone. Just holding the ice cream cone in your hand does not mean that work is occurring. If you were to lift that ice cream cone from in front of you to your mouth, then that force of the upward motion is parallel to the direction of motion up to your mouth. But if you're just holding it and you're walking forwards and backwards or left and right, your force to hold that ice cream cone is going up, but you're walking this way. Okay, so if the force is perpendicular to the distance, work still is not done. So here's our simplest practice problem. The force required to move a chair 4 meters is 3 newtons. What amount of work is done? So we have work, force parallel, and distance. We are told that our force is 3 newtons and our distance is 4 meters. Now we are assuming that if this is our chair, we are pushing it from this direction, so it is completely parallel. So work equals force parallel distance. Work equals 3 times 4. Work is 12 joules. So that's pretty simple because all it is simple multiplication or division if you're solving for one of the other variables. Practice problem number 2 is a little bit different because now instead of moving left or right, we're going to be lifting something. So determine the work done by lifting 300 kilograms to a height of 0.9 meters above the ground. So again, our equation, work, force parallel, and distance. I know my distance is 0.9 meters. We're solving for work, so our issue is they don't give us newtons. So what do we place here? We can go back to a previous unit and use the idea that force due to gravity can be used because force due to gravity is measured in newtons and it uses mass, and since we're lifting something, it uses gravity. So mass times gravity, 300 times 9.8, and our force is 2940. So to lift 300 kilograms, we have to apply a force of 2,940 newtons because we have to overcome gravity to make that object move. So we now have work equals force parallel times distance. Work is 2,940 times 0.9. And our work is 2,646 joules. So left and right is really easy. It's just force times distance. Up and down, we may have to calculate the force first by using Fg equals mg since we are lifting an object vertically. Now, if you pay attention, it says the weight of the object is, and it tells you 3,000 newtons. That step has already been done for you. So that's really easy if the force is completely parallel to the distance traveled. But what happens if the force occurs at an angle, meaning not all of your energy goes into moving the object? So imagine pushing a crate down the hallway. If the force that you exert is horizontal, all of your effort moves the crate. So let's use this as a picture. You would have to push here. But if you are taller than the actual crate, it's not likely you're going to push from the exact side. In actuality, you might push it down and forward simply due to the fact that you are tall. Okay, so if your force is at an angle, only the horizontal component of the force applied causes displacement. That means that we are going to have to separate out this force into the x and the y components, and we are only going to use the x component to calculate our work done. This equation works for that. We have work equals force times distance times cosine theta, because what they're going to do is tell you that your angle is 20 degrees below the horizontal. So this leg of the triangle is still found using cosine. Okay, so we've done sine and cosine in the past. This should be nothing new. It just simply adds an aspect to our work equation. So here's another practice problem with that cosine theta. You pull a rolling suitcase with a force of 190 newtons at an angle of 35 degrees to the horizontal to displace that suitcase 45 meters. Determine the work. So work, force, distance, and we're going to put theta. We have 190 newtons, 35 degrees for theta, and 45 meters for the distance. Work equals force times distance, cosine theta. 190 times 45 times cosine 35. So you do need to make sure that your calculator is in degrees in order to do sine and cosine. If you go to radians, it's going to skew our answers. When you simply multiply this through, your final answer for the work done is 7,003.7 joules. Now, sign of work is important. Work is a scalar quantity, therefore direction is not needed when we express the value of work being done. But sign, in this case, does not mean direction. It means, are we adding work to the system, or are we removing work from the system? So positive work is done if the force exerted assists in moving the object. Meaning, if I am walking through the airport and I walk on one of those moving sidewalks, that would be considered positive work because it allows me to move faster. Negative work is done if the force exerted on an object hinders the motion of the object, meaning that it hurts it or slows it down. So for example, if you go on the wrong direction of the moving sidewalk, it takes a lot more effort of you in order to get to where you're going because the work is working against you. That would be considered negative work. Friction is also considered negative work because it slows an object down. So sign, when it comes to work, does not mean direction. It means, is it adding to the system or taking away from the system? So the last thing we're going to talk about in this video, it's going to be real quick, is power. Power is defined as the rate of change of work, meaning it is the amount of work done over a given time frame. Power is measured in joules per second, which is also called watts. So things that we're used to seeing that have watts on it are microwaves, light bulbs. Those all give an amount of power because it's work done per given second. Our equation for power is work over time, which we can do force parallel distance over time, or force times distance cosine theta over time. All of these are interchangeable because they calculate the same value. So you could use power equals this. We could ignore this middle section, do power equals force times distance divided by time, or we can ignore the first two and do power equals force times distance cosine theta over time. All three of these could work for the power equation. So last practice problem. A force of 890 newtons is used to push a large crate a distance of 12 meters in 22 seconds. Determine the power required of this motor. So power, force, distance, time. Force is 890 newtons, distance is 12 meters, time is 22 seconds, and power is our question mark. So I'm actually going to use that middle equation, force times distance over time, because we were given force and distance, not the work value. So power is 890 times 12 all over 22. And our power is 485.5 watts. So that just takes the previous equation and then you divide your answer by time in order to calculate the power. So in class, we are going to be practicing with work and power calculations, and we're going to work up to doing a lab, which you are going to be calculating your own work and power output while doing a couple simple things. All right, I'll see you then so we can practice and go over any questions.